Swayam Prabha. Digital India. Educated India.
Hello friends. So, in the previous lecture we have discussed regarding the digital relays, how it can overcome the problems that is faced by conventional electromechanical relay, and that is used by utility, and that is biased or percentage differential protection scheme. Now, if I use digital relays or numerical relays for the protection of power transformer, then the digital relay is connected like this. So, if I have any power transformer which I wish to protect, then the CTs are connected on both the sides, and secondary of CT signals are given to the digital relays or differential relay. So, the arrangement remains same, the only difference is that whatever currents we are going to give or that is going to enter to CT1 and whatever currents that is going to leave the CT2 here, and that currents how we are going to provide or how we are going to process inside the digital relay, that process is entirely different when we consider the digital relay compared to the electromechanical relay. So, let us consider one example to understand the working principle of digital relay. So, here I have considered the same figure, this is the winding of the power transformer, and I have considered CT on each side of the winding of the transformer, and I have connected one digital relay, that is 87 number is given. If any external fault occurs here, this is my external fault which is going to occur outside the range of the CTs, 2 CTs. So, in that case, if I consider or if I calculate the operating current in case of biased or percentage differential relay, this is given by I1 minus I2, whereas in case of digital relay this is given by the factorial addition of the two currents, that is I1 and I2. So, if I consider this current as I1 and this current as I2, then this currents that is given by one current is 5 angle 0 and the other current that is again 5 angle 180, because if I consider the dot here, then current entering and current leaving both are 180 degree out of phase. So, this current is 5 angle 0 and this current that is 5 angle 180 degree, because both are out of phase. So, your operating current that will be factorial addition of two currents I1 and I2, and then you have to take the absolute value. So, this value comes out to be 0. The restraining current in case of biased or percentage differential protection scheme, it will be I1 plus I2 by 2, but here in case of digital relay the restraining current IRT, that is nothing but the scalar addition of two currents I1 and I2. So, that is 5 and 5. So, that I am adding and divide by 2. So, again I will get the 5. So, as your operating current is 0 in case of external or through fault, maybe on this side or maybe somewhere here, then this relay is not going to operate. Now, let us consider the other case, that is the when fault occurs inside the transformer. So, this is the case of internal fault which is going to occur inside the winding of the transformer. So, if fault occurs here inside the winding of the transformer, then the operating current that is nothing but 5 angle 0. Now, in earlier case the direction is this, but when any internal fault occurs this direction reverses. So, it is like this. So, both the values I1 and I2 both are 5 angle 0 and your operating quantity comes out to be 10. whereas your restraining quantity remains as it is in case of internal fault, that is 5. So, as operating quantity is greater than restraining quantity, so this digital relay operates. Now, if I represent this operating quantity and restraining quantity of digital relay, so where the operating quantity is the vectorial addition and the restraining quantity is the scalar addition. If I represent this in terms of relay characteristic, considering restraining current on x axis and operating current on y axis, then we will have the characteristic like this. So, your operating current, that is nothing but the addition of two currents. So, here I consider this as I W1 and this as I W2. So, this you can write down like this, and in generalized way restraining current you can write down as the scalar addition of I W1 and I W2. Now, instead of writing this 2, I have written the k. So, this k is nothing but the compensation factor, and this k you can consider either 0.5, you can consider as 1, or you can also consider max of either I W1 and I W2. So, 3 possibilities are there, but most of the utilities they will consider k as 0.5. So, that is why this 2 1/2 that comes here. So, that you can consider. However, one also consider, and the third case is also possible depending upon the application. Now, if I consider this characteristic of differential relay on x and y axis with restraining and operating current, then the first point comes that is known as your I per unit, and this I per unit provides the compensation against magnetizing inrush current and errors in CT, and at the same time if there is an unequal lead length exists between the one side of the CT and the relay where it is installed inside the control room, then that compensation is provided by this thing. So, instead of starting from origin, this graph that is also going to start at some value. Then the second is the slope 1. So, here I have considered slope 1, and if I use only this characteristic, then this is the single slope characteristic of digital differential relay, and this slope 1 is required to avoid CT ratio mismatch, because as I told you CT on both the side of the winding of the transformers are different, they have different CT ratio. If there is a tap changing mechanism or tappings are provided, and if your transformer is on other than the nominal or fixed tap, then those things are also compensated using slope 1, and if any non idealities are existing between the two CTs like CT saturation characteristic, then also that can be compensated using slope 1. And the slope 2, if I further add from here to here, then your slope 2 is required just to avoid the maloperation of digital differential relay in case of heavy through fault, particularly when one of the CT saturates and other CT is working in the linear range. So, this is meant for this. So, if I use dual slope characteristic like this, and if any operating point comes here above this, then the relay operates, otherwise for any point somewhere here relay does not operate. Now, if I consider the digital relay which is used for the protection of power transformer, then it is primarily important that how we are going to obtain the filtering and measuring functions, because that we need to implement mathematically inside the digital relay. And if we implement these functions mathematically inside the relay, then obviously the accuracy of the digital relay increases compared to the previous electromechanical relay where we use biased or concerted differential protection scheme. When we use digital relay, it is recommended by most of the manufacturers that all the CT connections are in the Y fashion only. So, as I told you in the previous class that if I connect the CTs in delta fashion, then there are certain disadvantages like increase in burden, complex wiring, other things are also there. So, if we wish to avoid those disadvantages, then we have to go for Y connection of CTs, and it is recommended for digital relay by most of the manufacturers. Now, let us consider the first case where we can see that how the magnitude compensation is possible using some mathematical equation in case of digital or numerical relay. So, we know that relay acquires most of the current signals through CT, and CT secondary signals or juice are given to the relay, and then when the CT secondary currents are available, these currents are applied some factor that is known as tap scaling factor for each winding. So, for each individual winding we have this secondary currents that is applied by this tap scaling factor, and that is the main logic for magnitude compensation inside the digital relay. So, if we apply this tap scaling factor, then both winding currents either on LV side and HV side both are available at a common base or at common platform. So, generally both side winding currents are normalized before further processing, and if we do this, then external interconnecting transformers or ICTs are not required in digital relay, which are very essential in case of electromechanical relays, which we have discussed earlier. So, now let us see what equation we can use in digital relay for magnitude compensation. So, tap scaling factor is given by this equation, which is MVA into 1000 in numerator, where MVA is nothing but the power rating of the transformer. In the denominator we have root 3 multiplied by kV winding, where kV winding is the voltage rating of a particular winding in kV kilovolt, and CTR is nothing but the CT ratio of the connected CT on a particular winding. Now, to understand this magnitude compensation in a digital relay, let us consider two examples. So, in the first example, I have considered one transformer which is 30 MVA rating. One side, that is LV side, is 11 kV and HV side is 132 kV, and on LV side the CT ratio is 1600 by 1, and on HV side 132 kV side the CT ratio is 200 by 1. For this transformer, if I calculate the full load current on LV side, then the full load current on LV side is given by I full load, that is nothing but the MVA rating, that is 30 MVA. So, 30 into 10 raised to 6 divided by root 3 into voltage rating on LV side, that is 11 into 10 raised to 3. So, if you calculate this, you will have the value, that is 1574.6 ampere. This current is available on primary of the CT. So, if you convert this, or if you transform or transfer this current on CT secondary side, this side, then the current available, that is 1574.6 divided by CT ratio, that is 1600 by 1. So, if you solve this, you will have the value, that is 0.9841. This value you will have, that is 0.9841. Now, if I go for the previous equation, that is tap is given by this MVA into 1000 by root 3 into kV rating of the winding into CT ratio, then if I put the value, the MVA rating is 30, in the denominator we have the kV on LV side is 11 and the CT ratio is 1600 by 1. So, if I put this value, I will have the value 0.9841. So, in earlier case, when we transform this primary current, full load current on secondary side of CT on LV side, we will have the value 0.9841, and if I use this equation, I will have the value 9841. So, if you divide this two, you will have the value, that is 1. Same way on secondary side, if I calculate the full load current, then I full load current on secondary side is given by 30 MVA divided by root 3 into 132 into 10 raised to 3. So, if you solve this, you will have 131.2 ampere, and if you transform this current on secondary side, then 131.2 divided by 200 by 1. So, you will have the value, that is 0.6560 ampere, and if you use this equation of tap, then you will have the value 30 into 1000 into root 3 in the denominator into 132 divided by 200 by 1. So, if you solve this, you will have the value 0.6560, and you can see if you divide this by these two values, you will have the value 1. So, this is how the magnitude compensation is obtained if we use the digital relay. Now, here you can observe that primary of the CT, that is here 1600 and here 200, these two values are different. However, secondary of the CT on both the sides are same. Now, let us consider second example when the secondary of the CTs are also different. So, primary and secondary values of the CTs on both the sides, they are different, and in that case let us see how we can obtain the magnitude compensation. So, in that case if I use let us say another transformer 250 MVA 66 by 132 kV, and this transformer is delta star 1, and if I use this, if I calculate similar way the full load current, then on this side I will have the full load current, that is nothing but 250 MVA into 10 raised to 6 divided by root 3 into this side is 66 kV. So, 66 into 10 raised to 3. So, you will have the value 2186.9 ampere, and if you again transform this current on secondary side of this CT, then you will have 2186.9 ampere divided by CT ratio, that is 2000 divided by 5. So, you will have the value that is 5.4672, and if you calculate the value using this equation of tap, then you will have the MVA, that is 250,000, in the denominator you have root 3 multiplied by kV rating, that is 66, and CT ratio, that is 2000 by 5. So, you will have the value that is 5.4672, and if you divide this two, you will have again the one value. Same way on secondary side, if you calculate the full load current, you will have the current this, and if you transform this current, you will have the value that is 1200 by 1. So, you will have the value that is 0.9112, and using tap also you will have the same value, that is 0.9112, by putting the value that is this 2, because this value remains same, right, here also and here also. Either you calculate on LV or HV side, the only difference is these two values. So, if you change this, you will have the value this, and here also you will have same value, and if you divide, you will have the one value. So, either we consider the change in primary side of the current or secondary side of the current, if both are entirely different, then also we will get the appropriate compensation in the magnitude in case of digital relay. Now, the second case we need to consider, that is the zero sequence filtering or zero sequence compensation. Now, to understand this, let us consider one delta star transformer. So, this is your delta winding and this is your star winding, and I have connected 3 CTs here. I have also connected 3 CTs here. Now, if I use conventional scheme, as this is delta winding, so this three CTs are connected in star, and then this is a star winding. So, these 3 are connected in delta. But in case of digital relay, we are connecting both these CTs in star fashion to avoid the disadvantages of delta winding. So, in that case we know that if there is a fault which is going to occur on star side on one of the phases which involves ground, right, this is a fault which involves ground. So, in that case the current will flow like this. So, this current, because whenever any fault occurs which involves ground, zero sequence current is always present, and that zero sequence current will flow like this, and that is also going to flow through these CTs. And as these CTs are connected with the relay, so those currents are reflected inside the digital relay. On the delta side, if you consider these currents are going to circulate inside the delta winding, but it will not comes out of the delta winding. So, current through these CTs, there is no zero sequence current, hence there is a mismatch, because whatever currents you are going to give from this side to the digital relay, and here this side, on one side zero sequence currents are present, on another side they are absent. So, there is a mismatch. In digital relay we have to compensate this also, and particularly this type of mismatch is going to occur when we have a delta winding on one of the side of the transformer, like star delta 11, star delta 1, delta star 1, delta star 11. So, these are the some common vector group we are using in case of power transformer, in all these cases we need zero sequence compensation. Now, to understand the effect of zero sequence compensation, let us consider one example. So, here I have considered 100 MVA rating power transformer. The LV side rating is 20 kV and the HV side rating is 110 kV. Now, with this value, if I calculate the full load current of the transformer on LV side, so I full load on LV side, we will have the 100 MVA divided by root 3 into LV side, the voltage is 20 kV. So, you will have the value that is 2886.75 ampere. If I use the CT ratio on LV side, that is 3000 by 5, because when current exceeds 1000 ampere, the secondary should be 5 ampere. So, if I use this and if I transfer this current on secondary side, then we have 2886.75 ampere divided by CT ratio, that is 3000 by 5. Now, before we calculate this, let us consider the other side also. On HV side, if you calculate the full load current, then you will have the full load current, that is 524.86 ampere. So, you have 100 MVA divided by root 3 into 110 kV, and let us consider 600 by 1 ampere, that is the CT ratio on HV side. Now, if let us say that some A to ground fault is going to occur on HV side, which is star grounded, with a fault current of 2400 ampere. Obviously, this currents are going to flow through these CTs which are connected on HV side. If I reflect this fault current on LV side, which is delta connected, then that currents will be to 2400 multiplied by the turns ratio, that is 110 by 20, and that is divided by root 3, because when we move from this side to another side delta, we have to divide it by root 3. So, the current available, that is 7621, that is this current. So, this current is 7621, this current is 2400. Now, if I use this current, that is 7621 ampere, 7621, and if you convert this current on secondary side using 3000 by 5 ampere CT ratio, in secondary you will have the current 12.70. So, 7621 divided by 3000 by 5, you will have 12.7 ampere. If you calculate now using the magnitude compensation using tap equation, which is given by MVA into 1000 divided by root 3 into kV into CT ratio, using this rating of the transformer, then your tap value on LV side you will have 4.811. So, if you divide this secondary current by this value, you will have the current 2.64, which is not 1. Same way, on the other side, if I use 2400 ampere current and if I convert it into secondary side using 600 by 1 CT ratio, we will have 4 ampere, and if I calculate the tap on HV side, we will have 0.8747, because again we have MVA into 1000 by root 3 into kV. So, your kV is 110 and CT ratio is 600 by 1. So, you will have the tap value 0.8747. So, if you divide this secondary current by this tap on HV side, you will have the current 4.57 ampere. So, see that these two currents are not on common base. So, that is why zero sequence filtering is must when we use the digital relay, and specifically when the vector group in the power transformer is delta connected or when delta winding is involved. Now, let us see how this zero sequence compensation is achieved or obtained when we use digital relay. So, this can be achieved using some mathematical equation without creating any additional phase shift. So, we know that zero sequence current that can be defined or given by very common equation I0, that is your zero sequence current, that is given by addition of 3 currents of the 3 phases IA, IB, IC. These are the 3 phases, divide by 3. So, if I want any compensated value of current in any phase, let us say A phase, B phase and C phase, So, then I want A phase compensated current I A compensated, I want B phase compensated current, that is I B compensated, and I want C phase compensated current, that is I C compensated. Then in that compensated current, let us say in A phase compensated current I A compensated, I have to subtract 0 sequence current I 0 from the phase current of A, that is I A, and I 0 is given by this equation. So, we have to put this value here. So, we have I compensated in A phase, that is I A minus I A plus I B plus I C by 3. Same way you have the compensated value of current in B phase and C phase. So, this 3 equations I A compensated, I B compensated and I C compensated, that can be written as I A compensated. So, if you solve this current, then 3 I A. So, if you divide this by this, so you have 3 I A minus I A. So, we have 2 I A plus I B plus I C by 3. So, you will have this current, that is 2 I A minus I B minus I C by 3. Same way you have the equation of I B compensated, that is 2 I B minus I C minus I A by 3, and I C compensated, that is 2 I C minus I A minus I B by 3. So, if I write this equation in matrix form, then I have the 3 currents on left hand side, that is the compensated current in A phase, B phase and C phase, that is I A compensated, I B compensated and I C compensated, that is given by 1/3. So, this 3 that is common here. So, you have 1/3, and in A phase you have the coefficient 2 minus 1 minus 1. So, you have 2 minus 1 minus 1. In B phase you have the coefficient minus 1, 2 minus 1. So, you have this, and again you have in C phase you have minus 1 minus 1 2. So, you have this matrix, and then again that is multiplied with your 3 phase currents I A, I B, I C. So, your compensated value of the equation that is given by this matrix, and using this you can easily compensate the 0 sequence current in case of digital relay. In this class we started our initial discussion with the digital relay, and we have seen that how we can apply the principle of operating current and restraining current in case of digital relay, and we have seen that operating current is given by the vectorial addition of 2 key secondary currents, whereas the restraining current is given by the scalar addition of the 2 currents. Then we have discussed about the how we can implement those things if I use the digital relay for the protection of power transformer. So, we have started our discussion with the magnitude compensation and how mathematically using analytical equation we can compensate the magnitude in case of digital relay. Then we have discussed that when any fault involve ground, and if I have delta winding in any vector group of the transformer, then the 0 sequence path exists on one side and it does not exist on other side of the transformer winding. So, in that case we need 0 sequence compensation also, and we have discussed that using again mathematical equation we can easily compensate the 0 sequence quantities in case of digital relay. The third case we have, that is the phase sequence compensation in digital relay, and this we will discuss in the next class. Thank you.